Homework Solution 6.5. A practical transformer has the following parameters. Turns ratio of 100 to 1, a primary core resistance of 10, a secondary core resistance of 0.0015, a primary leakage reactance of 15 ohms, a secondary leakage reactance of 0.002 ohms. Determine the voltage delivered to a load where ZL is equal to 25 plus J15. If the voltage input to the primary side of the transformer is 480 volts. So this is the first homework example that deals with practical transformers, where we're modeling the phase shift caused by the transformer coil, the power loss caused by the transformer on both the primary and the secondary side. So the givens in this problem statement are obviously the turns ratio, NP to 100 is equal to 100 to 1, a step-down type transformer. We've got the primary core resistance R1 is equal to 10 ohms. The resistance of the secondary is 0.0015 ohms. The leakage reactance of the primary, XL1, is equal to 15 ohms. And the leakage reactance of the secondary, XL2, is going to be equal to 0.002 ohm. We've got a load. We were told the whole thing was 25 plus J15 ohm. And then we've got the voltage input to the primary, so VP is 480 volts. We are asked to determine the voltage across the load. Find VL, right? Determine the voltage delivered to the load. So the solution to this, a little wonky there. The solution to this problem is we just start by drawing the practical transformer model. We don't have any magnetizing reactances or core loss resistances, so we are going to ignore those and use the simplified practical transformer model. That is this right here. We have the primary side circuit. These terminals right here represent the input to the transformer. So this is the source voltage, Vs. This here is the input to the transformer, Vp. We then model the internal parameters of the primary side coil with a resistor in series with an inductor. This is what we're referring to as the core loss resistance of the the coil resistance of the primary. So this was 10 ohms, R1, and this is XL1, the leakage reactance of the primary. XL1 was J15 ohms in this situation. Then what we do is we throw in a ideal transformer, plus minus, and a lot of times we call this VP prime right there. There's the primary side of the circuit. So everything from here over actually represents the transformer. Since this is a series circuit, IP here flowing out of the source voltage is the same as the current flowing through the primary side of the ideal transformer. We do something similar on the secondary side. We draw an ideal transformer and we model its internal properties as R1. So in this case, it was, R2, 0.0015, right? 2 stands for the secondary side here. And then it's got a leakage reactance associated with the secondary, which was J.002 ohms. So then we had our load that was connected to it. ZL is equal to, what was ZL? 25 plus J15. So that looks good. And the only thing we need to update here is that since this represents the secondary, those two terminals are the secondary impedance, or secondary voltage, Vs. A lot of times this here is called Vs prime. to let you know that that's not actually the output voltage of the transformer. So since this is a circuit, series circuit IS, we don't have to do anything special about that right there. So I just noticed that I've got a error here. The load impedance is not supposed to be 25 plus J15. It's supposed to be 0.25 plus J0.15 ohms. So the answer I gave in the solutions file is for 0.25 plus J0.15. So I'll go ahead and change that. 0.25 plus J0.15. I also put a little note at the very beginning of the video so that that's not too confusing. So anyway, we've got the load updated now. So what we need to do to solve this circuit to determine this voltage is we need to figure out what the current flow is in the primary. Then we can refer that to the secondary. That's a pretty easy way to do it. Or we can determine what the voltage is in the primary and refer that to the secondary. Either way, we need to refer all of this circuit to the primary to solve that. So to do that, I'm going to refer the transformer characteristics to the primary, and I'm going to refer the load over to the primary. You can do that in one step, add those together, and then multiply by the square of the turns ratio. I'm not going to do that. I'm going to leave them separate. You'll see why in a second, but I'm going to leave those separate. And the circuit that I'm going to solve is going to be VS, and then we've got the impedance of the primary side, ZP, and then I'm going to refer over the impedance of the secondary side, so that gets a prime because it's referred, and then I am going to refer over the load, ZL prime. This is going to be equal to VP prime right here. This is right here is VS, which is also VP, the primary input. And then this here is going to be this voltage right here referred to the primary, so that's going to be NP over NS times VS. So anytime I refer a voltage over, I do it by the turns ratio. So since this is VS, I refer it over to this side by multiplying by NP over NS. So that's this voltage right here. That's why I left them separate. It allows me to isolate the secondary voltage in one step right there. Since these are in series, that is still the primary current right there. So I just got to calculate what these values are. ZS prime is going to be equal to ZS times NP over NS squared. It's an impedance, so we multiply by the square of the turns ratio. Turns ratio in this problem was 100, so we get 0.0015 for R1, 0.0015 for R2, excuse me, plus J 0.002. We need to multiply that by 100 squared. So that gives me 1.5 plus J2, I believe. Good thing I checked that. It's ZS prime is going to be equal to 15 plus J20 ohms. So that gets substituted in for that block there. Now I need to refer the load impedance over ZL prime. It also just gets referred over by the turns ratio squared, so that's ZL times NP divided by NS quantity squared. So using my updated values, that's 0.25 plus J 0.15 times 100 squared. So I get 100 squared times 0.25 gives me 2500 plus J 1500 for ZL prime. So I can plug these values in for these boxes right here. Now I can use any technique that I want to analyze this primary side. At the end of the day, what this problem asked for was VS, so I'm going to solve for NP NS over VS as a circuit parameter right here. I'm going to solve for that voltage right there. And so I'm going to use a voltage divider formula to do that. NP over NS times Vs. So the voltage here is going to be equal to V primary side times ZL prime over the sum of the three impedances in series right there. ZP plus ZS prime plus ZL prime. So that was a pretty easy way to solve for the secondary voltage that way, and I can just rearrange this by saying Vs is equal to Ns over Np Vp ZL prime over Zp plus Zs prime plus Zl prime. So I can say Vs is equal to the inverse turns ratio. Turns ratio was 100 to 1, so inverse turns ratio is 1 over 100. Then the primary input voltage was 480 volts at an angle of 0 degrees. Calculated ZL prime right here, 2500 plus J 1500. Now I need to divide that by ZP, which I've forgotten, to be honest with you. Let's see, 10 plus J 15. Plus the secondary impedance of the transformer referred, so that was 15 plus J20. Plus our reflected load impedance, which was 2500 plus J1500. So there I've got my voltage divider, and I've got the supply voltage is going to be very low, 4.74 volts at an angle of negative 0.33 degrees.